Take it away, Liz.
Thank you very much. Thank you so much to all of you for coming in and choosing to watch some CLI demos instead of drinking refreshing beverages in the sun, at least for a few minutes. Right? Oh, yeah. OK, so I hope this sounds OK. It sounds a bit weird to me, so start waving from the back if you can't hear me. My name's Liz Rice. I look after open source at Isovalent, which is the company that created the Cilium project. Anyone here familiar with Cilium? OK, quite a few of you. Good. Cilium is built on a technology called eBPF, which I will be talking about this afternoon. And I'm talking about it specifically for use in security observability. And this topic brings together two areas that I'm really interested in. I've been interested in cloud native and container security for quite a while. I love eBPF, and I love the potential that it has for building some incredible new tools for not just security, observability, networking, and essentially instrumentation, particularly in a cloud-native world. So maybe hands up if any of you have even heard of eBPF before. Quite a lot of you. Anybody feel like you're an expert? I'm not even sure I'm going to put up my hand, no. I know a little bit. So first of all, the acronym stands for Extended Berkeley Packet Filter. Honestly, that's not a terribly helpful thing to remember, because you can do so much more with it than packet filtering. So put that out of your mind. All you need to know is that eBPF allows us to run custom programs within the kernel. It's a little bit analogous to how JavaScript allows us to make static web pages into something that's dynamic, that we can change how it behaves dynamically. So with eBPF, we can change how the kernel behaves dynamically. So I should probably just make sure we're all on the same page about what we mean when we're talking about the kernel. The kernel is the part of the operating system that interfaces with hardware. So it has the privileges to talk to hardware devices. As developers, we usually write applications in user space, but whenever we want our application to do basically anything interesting, be that writing to a file or displaying something on a screen or sending a network message, anything useful requires assistance from the kernel. And our user space code asks for that assistance using an interface called system calls or syscalls. You may not have used that interface directly because programming languages give us higher level abstractions that make it easier to use that interface. But even if you've never heard of it, trust me, every time you read or write from a file or display anything, send a network message, all of these things require the syscall interface. Now, all of these things are happening in the kernel, and we can attach eBPF programs to events. What do I mean by an event in the kernel? Well, it could be these system calls. It could be the entry or exit from any function. It could be any trace point. It could be network packets arriving. These are all examples of events that we can use to trigger our eBPF programs. So I think at this point we should probably see some real eBPF. Is that big enough, or shall I make that a bit bigger? Maybe one more bigger. OK. So this is the hello world, or let's change it to hello Amsterdam, of eBPF programs. This part here is the actual eBPF code. It's a bit of C program. All it's going to do is write some tracing, hello Amsterdam. The body of this code is my user space code that's going to take that C function. It's actually going to compile it. It's going to attach it as a K probe, a kernel probe. So there's the name of the function I'm going to attach. I'm going to attach it to a system call, and the system call I'm going to use for this example is execve, which is the system call that's used to run an executable. So every time a new executable program gets run on this machine, my tracing should get triggered. So I need to be root to run this, but hopefully we should start to see hello Amsterdam. Woohoo! There's lots going on this particular virtual machine. Things like Node are running. It's running in the cloud and measuring some CPU usage. So lots of things are triggering my eBPF program in this example. So, no, other way. A couple of things that I want you to notice about that. One is that we got some contextual information about whatever it was that triggered that program. In this example, we get the process ID and the name of the program that was running to trigger this execve. We get some timestamp and other flag information automatically included in this tracing, so it's clearly there and available to the eBPF program. Also, as soon as we loaded that eBPF program into the kernel, it automatically had visibility into all of those processes that were already running. We dynamically changed the way the kernel behaved. And this ability to spot things that are happening in processes that already pre-existed make eBPF really useful for tracing. And historically, a lot of the sort of early use of eBPF was for building eBPF tools, tracing tools. So a typical tracing tool is going to have some user space part of the tool itself. That's going to load an eBPF program into the kernel. It's going to attach it to whatever event it is that we want to trace. Maybe we're going to keep a counter of how many times that event happens, or maybe we're going to collect some information about every time that event happens. And we can store the information about those events, maybe incrementing a counter. We can store it in what's called an eBPF map. And the map is a data structure that we can share between the kernel and user space. We can use system calls to access data from this eBPF map. We could also share it between different eBPF programs. So our tracing tool can read the information from this map and show it to us as users. So this is essentially how a whole family of tracing tools work. And this family is from a project called BCC. Personally, I think when I first saw this diagram, I thought, this is terrifying. I have no idea what it's showing me. So don't worry if that's your reaction. What it's showing is dozens of different tools that have been built to use eBPF and that follow a very similar model to collect information about a whole variety of different things happening in a system. So if you want to collect metrics about how your network performance is going, or you want to understand how your file systems are behaving, there's probably a tool that pre-exists in the BCC project to help you gather these metrics. Let's take a look at an example. We'll use OpenSnoop, which is going to tell us every time a file gets opened on this machine. So I think it's here. OpenSnoop. Oh, I need to be root, of course. OK, and we immediately start seeing that there are lots of files being opened on this machine. So we're getting this really useful information, and as you saw, there are dozens of other examples that could give you exactly the information you need to understand performance in your system. But what does it mean in a Kubernetes environment? How many people are using Kubernetes here? I'm surprised you haven't all got your hands up, but OK, I believe you. So in a containerized environment, Kubernetes or not, we run our application code in containers. In Kubernetes, those containers are running inside pods. However many containers we have on a virtual machine, there is only one kernel per virtual machine, or bare metal machine if we're doing it that way. So all of our containers on the same host share the same kernel. And just like any other application, if they want to do anything that involves any kind of hardware, they're going to have to use the kernel to do it. They're going to have to use the syscall interface to send or receive messages or to read data out of files. Kubernetes is going to have to use the kernel every time it wants to create a new container. So the kernel is aware of everything that's happening on that host, whether it's in a pod or not. And that means we can write eBPF programs to observe what's happening across the whole host. And we don't have to change the pods, we don't have to change the application, we don't have to change the configuration. We just load the eBPF program into the kernel, and hey presto, we can see what's happening in all of those pods. So there's an example I'm going to use on the command line called inspector gadget, and let's bring this up. So actually, let's do it like this. Oops. There we go. So I've got a few pods running on this kind cluster. And if I were to exec into one of them, we can immediately see that this is the kind of OpenSnoop equivalent in Kubernetes. The inspector gadget tools have been very much inspired by those BCC tools that we saw earlier, but they bring them into the Kubernetes world. We get this additional information about not just what file's been opened, but what pod it was, what container, what node it's running on, and so on and so forth. So if I were to open a file from inside this pod, we can see that we get that information. Doesn't seem amazing from a security perspective that I can edit that file. So maybe if I was in charge of security for that X-Wing fighter, I would probably want to do something to harden that. We'll come back to that. So we've got information about what's happening. We've combined it with Kubernetes contextual information. And there are other tools that do similar things, but maybe present information in different ways. There's a project in the CNCF sandbox called Pixie that uses eBPF, again, inspired heavily by BCC project tools, gathers together lots of metrics, information, combines it across the Kubernetes cluster, and shows you some really nice graphical displays of that information. This example is showing a flame graph of how CPU is being used across the entire cluster, which I think is pretty cool. Another example of an observability tool in Kubernetes would be the Hubble component of Cilium. So this uses an eBPF program to report on every network packet that flows in the cluster. And then it can combine that into flow diagrams like this, well, this service map. We can see how different services are communicating with each other. We can parse the individual messages. We can see if messages are getting dropped. And we're also getting metrics that allow us to report on things like latency or the number of errors, or you name the metric related to networking, it's probably there. And I've started using the term observability now rather than tracing, because I think tools like this allow us not just to kind of gather the data, but they allow us to ask meaningful questions about what's happening in our systems. We can, for example, use that service map to understand which services are talking to which other services, or maybe to debug issues if we have connectivity issues in our cluster. We can use that flame graph to understand which of our applications maybe are resource intensive. So this is becoming much more the world of observability. So how does observability differ from security observability? And to me, the difference is a policy. We have a policy that defines the difference between what's normal behavior that we expect and what's unexpected behavior that might be malicious. We don't necessarily want to report on every single time that an application opens a file. We want to report when an application unexpectedly opens a file. Maybe that's going to be an indication that the application or the pod that it's running in has been compromised and that an attacker is accessing data that they shouldn't. In order for this really to count as observability and to count for kind of forensics, we need to understand not just that a security relevant event occurred, but we also want to be able to understand why it occurred, how it occurred, get back to what compromised this application or the pod or whatever bad thing has happened. And to do that, we're probably going to need some contextual information about that event. And as we've seen, eBPF is really great for collecting the contextual information as well as the information about the event itself. So for security observability, we want to collect information about events and compare it with policy. The kind of events that we care about are the kind of events that require assistance from the kernel anyway. We want to be able to detect unexpected network traffic. We want to be able to detect unexpected access to data, whether that's in memory or in files. We want to understand when executables are run. Perhaps if a cryptocurrency miner was started in our cluster, we'd like to know about it. And we want to know about the privileges that our processes have, and particularly if those privileges change, and perhaps that's indicating a compromised pod, some kind of attempt at a container escape. So of course, this is the kind of activity that we can observe with eBPF. Hooray. We've seen quite a few examples where we've observed this kind of activity by checking syscalls. In Hello World, I used the execve system call to show us when executables were running. OpenSnoop used the open family of system calls to tell us when files are opened. This is fine for kind of regular observability, but there is an issue if we're building a really serious security tool. And there were a couple of talks last year that really discussed this in detail. The problem is that if we look at the entry to a system call, we're looking at parameters that have been passed in from user space. When the kernel's going to actually do the thing that it's going to do, it has to copy the information from those parameters and build a kernel data structure. And there is an opportunity, it's what's called time of check to time of use vulnerability. It's not really a vulnerability because it's the kernel working as intended, but there is an opportunity for an attacker to modify those parameters after we've looked at them, but before the kernel has copied them and built up its data structure. If we're really serious about detecting security-relevant events, we need to make our checks later after the kernel has copied that information into the kernel, and we're looking at the data structure as the kernel is going to act on it. Now, there is an interface in Linux at precisely the right kind of point, and it's called the Linux Security Module interface. Has anybody used SE Linux or AppArmor? A few hands. I feel sorry for you. I know it's painful. Those tools like that and other security modules use this interface to make checks at the appropriate time. It's a safe place to check whether this particular file access is permitted, for example. So, wouldn't it be awesome if rather than having a kernel module to do that, we could use eBPF modules to make those checks using the LSM interface? And we can. There's a thing called bpf-LSM that does precisely this, allows us to hook eBPF programs to these LSM function calls. And that has the benefit that we can change how the eBPF program is behaving dynamically, so we can be much more flexible about the kind of policies that we want to implement. We can load these into a system that's already up and running. We don't need to reboot the machine or anything. We immediately get the benefits of protection on any pre-existing applications that happen to be running. So let's take a look at an example of this. For this example, I'm going to change the permissions on a file. So I pronounce it chmod. I don't know if everybody else says that. I say chmod. And I've actually got two programs here. The first one here is going to be attached to the system called entry point. And we're just going to get some tracing. And then I've also got a program that's going to attach to the LSM entry point. And what we get here is a data structure that's got the information that the kernel's going to use to identify the file that it's going to actually attempt to change the permissions on. So it's going to write to this trace pipe. I'm going to just run it from here. So it should be writing trace into here. And I've got a file called Liz. If I change the permissions on it, we should see two lines of trace, one from the entry point and one from the LSM interface. And there they are. And we can see that it correctly picked up the name of the file that I've just changed. One interesting thing that I tried on this is that I can fail that call. So I can return a non-zero error code, return code here, and that would prevent the change of permissions. But I didn't show that in the demo because it then prevented anything else from changing any permissions. And it turns out that when you're doing things like compiling, quite often that invokes some changes of permissions. So it kind of messed up my system, and I'm not going to show that. We'll save that as an exercise for another talk. So this seems brilliant, right? We can safely make these checks at an appropriate point. The only problem is, and we have this data, we have the access to the kernel's data structures that we can use to make intelligent checks and flexible policy decisions. There are two issues with this. The biggest one being that bpf-LSM was introduced in the Linux kernel 5.7, and not many of us are using 5.7 yet, and we probably won't be for a while to come in production. I'm sure some people are, but not everyone. Also, it didn't immediately come with the benefit of Kubernetes contextual information. And if we're going to use this for security observability, we want that contextual information. So Cilium project has tons of experience in eBPF and tons of experience in this Kubernetes world and getting hold of Kubernetes information. And And also tons of experience working in the kernel, because a lot of the folks who work on Cilium are also working on eBPF in the kernel. That interface, the LSM interface, is guaranteed to be stable. The system call interface is guaranteed to be stable. In other words, new future releases of the kernel will provide those interfaces unchanged, or at least in a back-compatible way. But that doesn't mean to say that every single other line of code in the 30 million odd lines of code in the Linux kernel change dramatically every release. A lot more of the kernel is pretty stable. It's just not officially stable. It's not declared as a stable interface. But there are plenty of function calls that don't change and haven't changed for years and are unlikely to change for some time to come. So if we can't use the LSM API, we can still hook into other function calls that are in the right place and are kind of de facto stable, even if not guaranteed. And that's what we've done with a project within the Cilium family called Tetragon. So rather than hooking directly into the LSM API, we're hooking into other sufficiently stable functions that are late enough that we have that safe kernel data structure information to act on. And we also have this knowledge from Cilium about how to map between processes and the Kubernetes identities that they relate to. You might be wondering why it's called Tetragon. Tetragoniska is a family of bees, and you've probably noticed that EB is our mascot for eBPF. The logo is, we're all about the bees. The Wikipedia entry for Tetragoniska has this really nice description about how they build small and unobtrusive nests and produce large amounts of honey, which I think is a nice metaphor for a low overhead tool that produces a lot of really great information. I've nearly said sweet information, but that seems to be pushing the metaphor a long way. So, Tetragon it is. This is a kind of extract of a tracing policy that I'll show you. fd install is the function that we're using. This is a kernel function for installing a file descriptor. So when we open a file, the kernel has a file descriptor that kind of is the identifier for that open file. The policy says we're only interested in files that are under /etc/. And there's some continuation, other parts of this policy that essentially say, OK, follow this file descriptor, report on read and write events that relate to this file descriptor, and then when we close the file, you can stop following. So that's the kind of definition of what we're going to do. We're going to be interested in events that relate to files in the /etc directory. And I think, let me just check that this tracing policy is already installed. OK, so it is. Tetragon runs as a daemon set, so there's an agent on every node reporting events that match these policies. And we also have a Tetragon command line that can take those events and present them in a really nice fashion. So here's my command. So the first part is essentially going to take the tracing output from Tetragon, and the second part here, Tetragon Observe, is going to show us events that relate to the default namespace. And there's some events that have already happened in the past while we were not looking at Tetragon, because the policy was already in place, including, you can see, when we opened etc password, that was reported. I'll do it again, just to kind of prove it. And I don't know if you saw it, but it did report it again. And if I, let's delete hello again and go, hi, Amsterdam. And if I write this, we'll see we got information about the fact that it was written and how many bytes it wrote. That's kind of useful. So you can imagine using that to alert on the fact, hey, somebody has written to a file in /etc. And it was this, it happened in this Kubernetes pod, and it was this executable. And this is actually just a subset of all the data that's reported in those logs that I mentioned. So we've got reports of events that are outside of our policy, and we've got the Kubernetes information that gives us the context to make this really useful. If you combine that also with information about networking events, this gets really useful for network forensics. So in this screenshot here, there's a kind of suspicious-looking domain name there, something, something, not reverse shell, honest governor. And if you saw something like that, you might want to know what was the executable, what was the pod, when did it start running, and use that to figure out how that pod was compromised. So we're getting this security observability. Can we use this also to prevent security? When we detect the likelihood that something's going to happen, can we stop it? We can with eBPF, at least in certain circumstances. Network policy, I mean, Cilium has been implementing network policy in eBPF for literally years. It does this using eBPF programs that run every time there's a network packet, inspects the network packet, sees whether it's in or out of policy, and if it's out of policy, it just drops the packet, and then the packet will not flow. So there are certainly historical precedents for using eBPF to do security enforcement in runtime. But if we're using K-probes on system call entry points, it's not quite as straightforward. I did say that if I failed, or if I sent a non-zero return code from my chmod example on the LSM API, the Linux Security Module API, I could stop the permissions being changed. But if I'm observing a system call entry point, it doesn't actually matter what return code you give. The kernel will carry on and process the system call regardless. So you can't stop that from going ahead. The approach that most eBPF-based security tools have taken up till now is to go, OK, I can see this out-of-policy event. I'm going to send it to user space, and I'm going to have user space do something about it. Maybe it's going to kill the process or the pod. But the problem is, in that period of time between asking user space to get involved and then user space sending the kill message, and time has passed. Data may have been exfiltrated. Even worse, the malicious actor might have installed some kind of persistent threat on the machine. This is enough time for bad things to happen. What we've been able to do, thanks to some pretty serious kernel understanding in Tetragon, is to send the sigkill in immediately from the kernel to kill that process immediately. And this is happening sort of synchronously before the event has been able to be processed. So I've got an example of that. If I've got two versions of my policy, one of which adds this, if it happens, kill the offending process. So I'm just going to apply that version of the policy. Kill. All right. I'm in the same pod. I've not changed the pod. I'm going to try the same thing that I did before, and I'm going to try and edit this file again. And I can open it. Oh, I need to run Tetragon again, because that will be good. So we can see that when I ran vi, it opened the file. Presumably, it read the whole thing out and then closed it again. And let me, oops, wrong window. Let me try to write something else. So when I opened this file, it had Hi Amsterdam in it, but it didn't have something else in it. Let me attempt to write that. So we can see killed here. We can see sigkill there. We can see that the attempt was made to write slightly more bytes than we wrote earlier. So it's definitely had a go. What happens if we look at the file? The file does not have something else. We killed the process before it was able to complete that write operation. Which I think is awesome and deserves a round of applause, right? So I hope that you'll agree that eBPF is a really powerful platform for building all kinds of tooling, whether that's about observability, whether that's about networking, whether it's about security. We have this ability to instrument our applications dynamically. We don't have to change the app. We don't have to reconfigure the app. We can collect all this really useful contextual information, particularly in a Kubernetes environment. That's super useful for forensics. And we even have this option to enforce directly from within the kernel, which I think is pushing the boundaries of what we're doing with eBPF forward quite a big step. So if you're interested in eBPF, there's a couple of downloads that you can get from the Isovalent site. One is a book generally about eBPF, another one written by a couple of colleagues of mine that dives into this security observability concept and Tetragon in more detail. Everything is open source, it's online. You will find us on the Cilium website or the eBPF website as well. And we also have an amazingly active Slack that covers both Cilium and eBPF. Either of those websites will take you to it, where you can engage with loads of people who are, like me, really enthusiastic about eBPF. So with that, thank you for choosing to watch some demos. It won't be long till you get that refreshing beverage, I'm sure.
Thank you so much, Liz.